Hello everybody and welcome back. Root Beer here looking at B3 on the 2014 Canadian Open or COMC paper. Alright, so what have we got? 5 X's and 4 O's are arranged in the below grid. That's odd. Usually I would say grid below, but that's fine. Such that each number is covered by either an X or an O. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we've got some X's and some O's, something like that. There are a total of 126 different ways the X's and O's can be placed. So there's one of them, for example. That's kind of interesting. I wonder how to show the 126 there. That'd be interesting. Probably choosing where the O's go and then the X's have to go in the remaining places. Anyways, of these 126 ways, how many of them contain a line of 3 O's and no line of 3 X's? A line of 3 in a row can be horizontal, vertical, or one of these diagonals. Interesting. So how many of them contain a line of 3 O's? No line of 3 X's. Interesting. So let's sort of try and reason our way through this. If we had a line of X's, where could it be? Well, we could have one of the diagonals, or we could have a column. I mean, I'm really just restating what they've told us in the problem. Or we could have a row, say the middle row, something like that. Okay. But in order to block this, in order to make sure that I can't do a row, so in order to block such a line, say the rows, how do I stop there from being a row of X's? Okay. Well, I could have, say, an O somewhere down on the bottom row, but that wouldn't stop me from placing some X's along the middle row, so I need an O in the middle row. Doesn't matter where, but I need an O in the middle row, and then I can't put a row of X's. And then how do I stop a row of X's on the top? Well, you need an O there. So this placement of O's sadly doesn't satisfy the line of O's that we're looking for, and that's fine. But it stops rows of X's from happening. So this is an important thing to realize. It doesn't stop the diagonal of X's that could happen. It doesn't stop a column of X's. But in order to block rows, we need an O in each row. In order to stop the columns, you need an O in each column. In order to stop the diagonals, need an O on each diagonal. And I think the diagonals might be the easiest thing to block, just because if you put an O in the middle, no way you're going to get a diagonal full of X's there. But these conditions are what we need to look for. So when I'm placing my O's, I need an O in each row. I need an O in each column. Okay. So now let's think about where we could place a line of O's. I think this is just going to break down into cases. So we might say case 1, an O. How many O's do we get? We get only 4 O's. So could we have an O row? A row of O's. Well, that sort of forces O's to go here, and then I only have one other O left. Now, I could place it up here, I could place it down here, but I will leave a row unguarded. I only get one extra O. And so as soon as I place that 4th O, somebody can come in and place 3 X's. So 0 cases. 0 cases will have an O row and no X rows. And so similar, in fact, these don't even really count as cases. It's just sort of observations, really. no row of O's, as fourth O can't block other two rows. Okay, similarly, I can't do a column line of 3 O's. Because if I did, again, I only have one O. And sure, I've blocked any rows, but there's always going to be a column available. So similarly, we can't do a column line of O's. And so this forces a diagonal line, if indeed this can be done at all. The answer might be 0. Okay? The answer could certainly be 0. But suppose I had a diagonal. Well, there's 2 diagonals we could have. You do this one. Or we could do this one. And as soon as I do that, well, there's an O in the middle. So there's no X's that we could place for the diagonals and have a diagonal line. And there's an O in each column and an O in each row. So there is no line of X's. And the same thing happens down here. O in the middle blocks both diagonals. There's an O in each column and O in each row. So no matter where I place the X's, we're not going to have a line of X's. So the question is, where can I place my last O? Right? And there's 1, 2, 3, 4, 5, 6 ways to place the fourth O here. And 1, 2, 3, 4, 5, 6 ways to place the other O down here. Now, if you're good at counting problems, you might be suspecting, is there any sort of overlap? Is there something I'm double counting? Like, is there a way to put the O's so that they're on this diagonal and on this diagonal, and that I'm secretly accidentally counting the same thing twice? Well, no. If we satisfied both cases, we'd have to have 5 O's, but we don't. We only have 4 O's. So each of these situations is unique, so we get 6 cases here, 6 cases here, and that's a total of 12. So 12 out of the 126. So about 1/10 of the time, you can get a line of O's and no line of X's when you fill this thing out. But the answer they want is 12, what did they call them? Situations or 12 ways. 12 ways, and that's what we would want. 12 ways. And we explain our reasoning below. Okay. So that's B3. We're going to finish off part B in the next video with B4. Feel free to join me for that.